to be. Today we are going to be discussing Raoult's law. The Raoult's law we are going to look at is actually going to be mixtures of liquids. And the most important thing here is, why is it that some liquid mix and some do not mix? What is the chemistry behind this particular phenomenon? So today we are going to look at Raoult's law. Raoult's law. And here we'll be looking at mixtures of liquids. Mixtures of liquids. Why do we have some liquid mix and some do not mix? For example, how is it possible that you turn milk, for example, into water? No matter the small the proportion, it is going to mix. But when you turn kerosene into water, it does not mix. What is the chemistry behind it? What did Raoult discuss about this sort of mixtures of liquids? But let us know what Raoult's law says. Raoult's law simply says that the vapor pressure of a particular liquid, let's say it's a solvent now, a particular solvent, in the presence of a mixture, which is of course a solution, is always equals to the vapor pressure of the pure substance, that is the pure solvent. For example, if you want to mix kerosene and water, what he is saying is that the vapor pressure of kerosene, or let's not of kerosene, of course, of instance of kerosene, perhaps if it mixes, supposing it was going to mix with water, the vapor pressure of kerosene in water is equals to the vapor pressure of that kerosene when it was not mixed with water. That is what it's saying, and you simply multiply that by what? The mole ratio, which is the proportion. That is what Raoult's law said. So he simply said the vapor pressure of a solvent in a solution or a mixture is equals to the vapor pressure of the pure solvent multiplied by its proportion, which of course is the mole fraction. Now he gave a mathematical interpretation of that. So according to Raoult's law, P A is equals to P O and then A and XI. By this is definition, it means that this of course is what? The vapor pressure of the mixture, and this of course is the vapor pressure of what? The pure solvent, and this of course is the mole fraction. And this mole fraction is simply defined as Na all over what? Na plus Nb, where of course N is the number of moles of the solvent you are using, and A is of course the type of solvent you are using. The same thing with B, because you require two solvents for you to now produce a mixture. Now this is his definition of what Raoult's law means, the mathematical interpretation of what Raoult's law means. But why are we interested in talking about Raoult's law when we say we are interested in mixtures of liquids? Yes, this is because the issue of the mixing of liquids came from the definition of Raoult's law. Now, Raoult believed that there are two types of liquids. He said there are two types of solutions, or rather, if you prepare solutions, there are two types. And according to him, one is an ideal solution, while the other one is a non-ideal solution. That is what Raoult's law says. Okay, he says that if you look at a solution that you prepare, whether it mixes or it doesn't, one of it will be an ideal solution, while the other one is a non-ideal solution. And according to him, the ideal solution always mix. So he said the ideal solution always mix, while the non-ideal solution does not mix. It does not mix. You see, that is why we began by talking about the Raoult's law before going to the main thing. And if Raoult's law simply explained the fact that ideal solution mix and the non-ideal solution do not mix, that means that the non-ideal solution are deviating from what? The Raoult's law. And if they are deviating from the Raoult's law, it can be positive or negative deviations. Now, if what is actually the ideal solution plots, let us know. Now, according to him, there is a plot in this way, and from here there is a straight line this way, and there is a dotted line this way, and here there is a dotted line to this point. According to Raoult's law, this is vapor pressure, of course, and this is vapor pressure. So it means that this side here is your mole fraction, the mole fraction. Now he believes that once you plot a graph of a mixture and the graph gives you this kind of appearance, it means that that solution is an ideal solution, therefore it mixes. But once you plot a graph that deviates from this kind of a plot, it means that it is a non-ideal solution. The solutions will not mix. They will rather form two layers, for example, kerosene and water. And now, he believes that a straight line of this form will always be the vapor pressure of the mixture. And this will be the vapor pressure of what? Of one of them, which let us say is hexane, okay, above the mixture. And this is the vapor pressure of, let's say, heptane above the mixture. So it means that here we are being precise now that hexane and heptane mix. And if they mix, they can form a solution that is an ideal solution. So we can have a possible plot of this format. That was his explanation of what ideal and non-ideal solutions are. But let us go to the main point. So why do ideal solutions mix and why do non-ideal solutions don't mix? Now, if we go to the main thing, there are two very basic reasons. There could be other reasons why solutions do not mix and they mix, but two basic points we have to raise here. And one of the points is the Van der Waals force of attraction. The Van der Waals force of attraction. Now, you've heard of that before. For every molecule, for all molecules that exist in every solvent, which is a particular liquid, there exists between them the Van der Waals force of attraction that holds the molecules together. So, at any point in time, you have liquid A, for example, hexane, and then liquid B, for example, heptane. If the Van der Waals force of attraction that bonds the molecules of hexane together and the Van der Waals force of attraction that bonds the molecules of heptane together are the same, those two particular liquid or solvent can mix. So it means that the mixing depends seriously on their individual Van der Waals force of attraction that holds the molecules together. That means kerosene and water do not possess the same Van der Waals force of attraction, and that is why they don't mix. They rather form what we call layers. That is it. So Van der Waals force of attraction is number one reason why molecules do what? Why solutions, or rather why liquids do what? Mix or they do not mix. Now, another reason why you could have certain solvents mix or do not mix is because of what? Of their entropy, and this free energy of mixing. Remember that we have, when you do colligative properties, you know that we have delta G equals to delta H minus T delta S, and these are all mixing. These are all mixed. These are all mixed. So it means that the delta G, which is the free energy of mixing, is equals to the free energy, the enthalpy of mixing minus that of what? Entropy of mixing. Now, for liquids to mix or not depends seriously on here and here. Let us look at it. If your delta G of mixing is negative and your delta S of mixing is positive and your delta H of mixing is near zero, that is more negative, this particular solvent will mix. It will do what? It will mix. It will show us this kind of a graph. That is the chemistry behind it. So for any type of liquid that will mix, the Gibbs free energy of mixing will be negative, and then the entropy of mixing will be positive, while the enthalpy of mixing will be near negative. That is about zero, if not zero. And that means that this kind of a solution will always be exothermic. Will always be exothermic. So it means that solutions where their solvents react to give an exothermic reaction will always mix, will always be what? Will always mix, and they will always be ideal solution and produce this kind of what? A plot that shows ideality. But a situation whereby the enthalpy influences the entropy and the Gibbs free energy of mixing such that the Gibbs free energy of mixing become positive and the enthalpy is more positive. That's an endothermic reaction. In that case, those solutions, those liquids will not mix, because the enthalpy is more positive, and then the entropy, the Gibbs free energy of mixing is what? Positive. Of course, it means that your entropy of mixing is also going to be what? Negative. In that case, you will not have the mixtures, you don't have the solvent mix. So let us define two things here. Raoult's law had said we have what? Ideal and non-ideal solution, and the ideal solution mix. Non-ideal solution don't mix. The non-ideal solution that don't mix deviate from what? Raoult's law. They will not give us a kind of a plot. But why do they not mix? Why do others mix? One, they mix because the van der Waals force of attraction for the individual solvents are the same. Two, they mix because they are able to mix because their entropy of mixing and the free energy of mixing is what? The free energy is what? Is negative. The entropy is what? Positive. And the enthalpy is what? Near zero. In that case, it's more like saying the enthalpy is zero and then the entropy is positive while the free energy is negative. So in this case, milk will mix with water. But where the enthalpy of mixing is having higher values, positive values, is more endothermic, you will expect the free energy to do what? To become positive. And then you expect what? The entropy to become what? Negative. In that case, you will not have the solvent mix to give you a solution. They will rather give you a partition solution. We will not waste much time to go into calculating this, how this influences these two. But in our next class, we are going to see how this influences these two to allow for mixing, for ideality, and to disallow for mixing. I hope you learned something great today. Why some liquids, why some solvent mix, and why some do not mix. Until our next class, do not forget to share, do not forget to like, do not also forget to follow, do not forget to subscribe at my YouTube channel, like and comment. It is bye.